Okay, welcome back. We are going to continue our march towards Shor's algorithm. I'm actually enjoying these lessons on gates. I was thinking, is there a way I can present Shor's algorithm just as a pure algorithm without addressing the idea of quantum gates? But it's really not fair. We're going to talk about quantum computing. People are going to look at all different resources, and quantum gates are just such an important part of that. I think it's fine to have a few of these lessons on quantum gates, and I'm kind of enjoying it anyway. So today I promised that we would go and do a deeper look at a pretty intricate circuit, a circuit that mimics the Toffoli gate and does so with a more complicated input that demonstrates entanglement. And so I like that demonstration. The last demonstration that we extracted the idea of the phase kickback, which is an important concept that if we didn't walk through the algorithm, I wouldn't have had a chance to show phase kickback. In fact, I didn't even realize it was in our face until I actually saw it there. And that's an important concept for phase estimation, which is a critical part of Shor's algorithm. So this is definitely worthwhile, even though we're not obviously addressing questions of factorization, of, um, of number theory, or of the quantum Fourier transform. So let's dive a little bit more into quantum gates, and let's begin. Okay, so our starting point will be, as we described at the end of the last lesson, this condition. We have three qubits, qubit 1, qubit 2, and qubit 3. And at various times in the algorithm, qubit 1 and 2 might be the target qubit of a C0 gate. And toward the end, qubit 2 is the target bit. Qubit 3 is never the target bit, but let us see how this circuit marches along. And the first step takes the 0 qubit, this 0 state, and runs it through a Hadamard gate. And what's interesting is that that immediately produces the same state we have in qubits 2 and 3. Remember, the 0 qubit through the Hadamard gate produces this exact superposition. You've got to kind of know that by now, right? You've got to kind of memorize that that's how the Hadamard gate works. And so at this point, at stage 2 of the system, you have a very, very important condition. The state of the quantum computer at point 2 in the system is this state right here. It is not entangled. It is still not entangled. We have factorized the first qubit, the second qubit, and the third qubit. So the way you know is any measurement on any given qubit doesn't affect the other two qubits whatsoever. But this state, when you see this state, when you see these, first of all, forget the normalization. That we're presuming that everything's normalized. I dropped the square roots of 2 here, but this would obviously have uh, 3 factors of the square root of 2 out in front, but we're ignoring that. But if you were to expand this whole thing, what you would get is you would get all of these states. This is 1, 2, 3, 4, 5, 6, 7, 8 states, right? Which is, of course, 2 to the third power, where this is the number of qubits of our computer. So our computer has 3 qubits, 2 to the third power. That's the total number of basis states that you need to describe an arbitrary state of the quantum computer. And what happens here is in this particular computer, or this particular circuit, I should say, right here at phase 2, at spot 2 of the computer, you have this product. And remember how this looked in our previous work on the quantum Fourier transform. We had a way of looking at the quantum Fourier transform, which was a tensor product of qubits, where in that circumstance there were phases that were introduced, and there were different phases on this on the excited state of each of the superpositions. But you still have this massive product, right? And in this case, you have no phases, and if you multiply it out, you just get the sum of every possible state of our quantum computer, right? There should be pluses. I have implied pluses here. So this is the total state. There's all these implied pluses, and there's an implied multiplication by 1 over the square root of 2 to the third power, right? So the state of the whole computer now is written like this. And this is super important because right now when you look at this, the in some sense the input, or very close to the input, it's not literally the input because this is literally the input, but very close right here at this point, for this particular arrangement, you have the quantum computer is looking into every possible state it could be in, and all the subsequent operations are going to operate on every possible state of the quantum computer in parallel, right? And this is when people talk about, oh, quantum computers can work in massively in parallel. This is exactly what they mean. They mean that this circuit is acting on all of the conceivable states of the quantum computer. Now imagine you had 100 qubits, right? Like there are quantum computers out there that have 100 qubits. They're not necessarily all input qubits, but regardless, I mean, it really doesn't matter. The state of the computer has, say, 100 qubits. Well, that's 2 to the 100th power, and then you have 2 to the 100th power basis states, and very quickly in the system, you put all of those basis states together into one massive state of the computer, and then the computer processes that massively, uh, uh, maximally superpositioned state of the computer. And to make the computer useful is you've got to winnow this down. So at the output of the computer, in this case, our little quantum circuit, you've got to winnow it down so at the output, everything kind of cancels out and only the answers you want are left behind, right? But anyway, we'll talk about that later. But the point is right here at state two, you've entered this maximal state of the quantum computer. And in fact, last time we were able to kind of track bit by bit. We did qubit by qubit, and we left them in this form. But in this exercise, we're actually going to go ahead and, since we only have 8 states here, we're going to blow up all states of the quantum computer and then run through the gates as they would act on each individual state of the computer. So this is what massive amounts of parallelism means. So this is a good exercise for that fact alone. But now we know what things are like at state two. Now state three is a C0 gate, and it flips the target bit is bit number one, and the conditional bit is bit number two. Well, all we have to do now is look at all of the states, and all of the states that have bit number two with a one in it, those states we flip the first qubit, right? So this one has bit number two is a zero, so nothing happens to this state. Bit number two is a zero, nothing happens to this state. Well, here bit number two is a one. So we are going to flip that bit, this zero to a one, and that's exactly what we do. We flip this zero to a one. And this one has a one, so we flip that zero to a one. This is a zero, so we leave it alone. This is a 0, we leave it alone. This was a 1, so we flip this 1 to a 0. And this is a 1, so we flip this 1 to a 0. So that is how the C naught works. But I'm actually going to now include, this is going to represent state 4. So we've done all the bit flips that happen at 3, but now we have to do this inverse Toffoli gate. And this happens for every one of these states, right? This isn't a conditional Toffoli gate. It's not like this, right? That would be conditional. It's not conditional. This Toffoli gate is thrown right there on the rail for bit number one. So for every, so now, but we know that it only affects bit number ones when it's, because when it's in the state, the excited state, when it's in one. So it provides no phase to bit number one here or here, but it does provide minus pi over 4 phase for all of these computer states, computational states that have a 1 in the first position. So these 4, right? These 4 pick up a phase of minus pi over 4. So now I'm no longer writing e to the minus I pi over 4, but clearly this means e to the minus I pi over 4. So that's my notation now for e to the minus I pi over 4. I'm just tracking the amount of phase that's in there. And that's just to make it a little easier to read and a little easier to write down. So this is the output of the quantum computer at position 4. It's that all of the states of the computer are still there, but now we've introduced this phase on some of them. So then now the next step is we are going to do the bit flip again based on the condition of the third qubit. So again, this, since we've broken down the computer into all possible states, right, we are now looking at the third qubit, and when the third qubit is in a state 1, we will flip the first qubit. So when the third qubit is in a state 1, we flip the first. So here's an example, right? The third qubit is in a state 1, so we flip the first to 1. Third qubit is in a state 1, we flip the 1 to 0. Third qubit's in a state 1, we flip the 1 to 0. Third qubit in a state 1, we flip the 0 to 1. Right, so that's easy. And then right after that, now that we have all those lined up, we execute we're executing the regular Toffoli gate, which again only shifts the first qubit if the first qubit is in the 1 state. And since we have all the states of the computer represented, I just go down and I look for 1 states, and then I add a T-gate phase shift of pi over 4. So that picks up a pi over 4. This one picks up a pi over 4. Notice this one already had picked up a minus pi over 4, but it persists in that 1 state to pick up another phase shift. So these two kind of cancel out. So here it shifted one way and then it shifted back. I'm not going to do the cancellations now. I'm going to wait till the end. But then this guy does not pick up a pi over 4, and it only has the minus pi over 4 picked up in the previous gate. And this one does pick up a pi over 4, and then this last one picks up its first pi over 4. So that's the state of the computer at position 6. Position 7, again, it's another C0 gate conditioned on qubit number 2. So we now look for all of the qubit number 2s that have a 1, and we flip those to 0. So this guy flips to 0. This guy flips to 1. So you're flipping the first qubit's state if the second qubit is a 1. So then here's the second qubit is a 1, so you flip that 0 to a 1. Second qubit is a 1, so you flip that 1 to a 0. Now notice how much more annoying this would be if we used this method of tracking everything. If I tracked every qubit individually, then it would just become much more difficult to do the swaps and do the analysis if I left it in this permanently factored form where I traced every single qubit by itself, right? Here I abandon that. I'm not tracing each qubit by itself. I'm tracing each state of the computer by itself. And so now I don't have to worry about, oh, what state is this actually in to execute each of these, or executing each of these twice for each incident of each component of the conditional qubit. By blowing up the whole computer, all I have to do is execute the logic in its most classical and natural way, because I've got every conceivable classical state written down. Now, I can do this because I've only got 3 qubits I'm dealing with, and my quantum computer only has 8 states. If I added a 4th qubit, my quantum computer would now have 16 states, and it would, eventually it's not doable by hand, and eventually it's not even doable by a computer, right? The idea is this grows so fast, right? This list of states grows so fast that eventually even a classical computer can't do it. And that's sort of the point, right? The point is I can simulate circuits all day. I'm simulating a circuit right now. I am simulating this circuit by hand. But you see what it takes me to do it by hand. You take L to be, a million qubits, right? If there's a million qubits in your quantum computer, then I have to write down 2 to the 1 million states of the computer. And then, yeah, I could calculate the phase of each state and put the phase in front of it, and then, proceed to the next one, flip the bits and do all that. And then I've simulated the computer. But at some point, this 2 to the L gets too big, right? It's growing exponentially, right? It's growing exponentially. So this is another way of sort of viewing that core fact of why we're doing quantum computers, right? In principle, the quantum computer does this all automatically, right? If you build a machine to do it, you won't have to track it. You're not ever simulating the machine. It's just running. Okay, so where were we? Trying to get to state 8. We're trying to get to this position. So I've just done all the bit flipping, so now I need to engage the inverse T gate, right? So I should get a phase of minus e to the minus I pi over 4 for every instance of our quantum computer where bit number 1 is in the 1 state, right? So I pick up e to the minus pi over 4 for this state because bit number 1 is in 1 state. Bit number 1 is in 1 state here. Pick it up here. This one already had 2, so I'm picking up yet another. So these two canceled each other's out, and then I put it back on for this state. And for this state, again, minus pi over 4 comes out front. This state is left alone. And notice this isn't conditional, right? Just as a reminder, this is not a conditional operation. This is a T-gate operation that's just right in the flow, right? It's not conditioned on anything. So then I'd repeat this again. I got to do another set of bit flips, this time conditioned on bit number 3. So I will look at this. So here bit number 3 is 1. So I will flip this from a 1 to a 0. Bit number 3 is 1. Flip this 1 to a 0. Bit number 3 is 1. Flip that 0 to a 1. Bit number 3 is 1. Flip that 0 to a 1. So that takes care of the bit flips. And then I have a regular T gate. And I actually have 2 T gates here in this phase, right? I've got 10. I'm shooting to position 10, so I've got to do these 2 T gates. One is a regular T gate on the first bit, and the other is an inverse T gate on the second bit. So on the first bit, I have an inverse T gate. So I get the inverse T gate applied. No, I think I have the regular T gate, right? Yeah, the regular T gate applied on the first bit. So I'll get a regular T gate here, a regular T gate here, right? It goes from minus pi over 4. There's the minus pi over 4 from the previous step. And then this is the regular T gate because of the 1, regular T gate because of the 1. And this one also has a regular T gate because of the 1. And then on the second bit, I have a inverse T gate. So here's the first one with a second bit is 1, so it gets an inverse T gate. Second bit is 1, gets an inverse T gate. Second bit is 1, gets an inverse T gate. And second bit is 1, gets an inverse T gate. And again, I'm not canceling any of these things out just yet. So that brings us up to step 10. Step 11, we want to now get to 12, right? So we're going to execute this conditional bit flip. It's the second bit is being flipped, conditioned on the third bit. And I think I did this on a separate page. Did I? Well, I know that, for example, this state here, this 0 here will become a 1 because the third bit is 1s and it flips the second bit conditionally. This one will become a 0. This one will become a 1 and this one will become a 0. And I had made some mistakes there, so I had to pause and correct them. But after those bit flips, this is what we are left with. And then we introduce the phase that we're interested in, right? So we've done these bit flips here, and now we are going to introduce this phase, this S gate. Oops, whoops, oops, oops. We've done these bit flips. Sorry. Yeah, you got to go through this very carefully. Yeah, we did these bit flips, and now we have to implement this other inverse T gate. Sometimes I make a mistake and call this a Toffoli gate, but this is not the Toffoli gate. This is a single qubit T gate. And so when we introduce that on the second bit, it picks up this, it picks up these. It picks up this phase here, because the second qubit is a 1. Second qubit is a 1. It's going to pick up this phase here. Second qubit is a 0. No phase is picked up. No phase is picked up. Second qubit is a 1, it'll pick up phase. Second qubit is a 1, it'll pick up the phase, and no phase picked up there. So it picks up that additional phase. So now we need to go from step 12 to step 14. Well, what do we see? We see we need another conditional flip, conditional C0 gate, conditioned on the third qubit, and then we execute an S gate or a phase gate. This is called, all these gates are introducing phase, but this one for some reason is called a phase gate. So then we introduce a phase gate on the second qubit and a normal T gate on the third qubit. So flipping the second bit conditioned on the third means this state, the 1, goes to a 0. This 1 goes to a 0. This 1 stays the same. This 0 goes to a 1. This one stays the same. This 1 should go to a 0. This 1 stays the same, and this 0 should go to a 1. And now we implement the phase gate as appropriate. So the phase gate is on the second qubit. And again, that only affects the second qubit if the second qubit is in the 1 state. And the reason we know this is because we've kind of got this memorized now. We've got it memorized that the phase gate, all these phase gates only really affect the excited state of any given qubit. So the second qubit is in a 1, it picks up a phase of pi over 2, right? Second qubit is a 1, it picks up a phase of pi over 2. Second qubit is a 0, so it picks up no phase. Second qubit is a 1 down here, picks up a phase of pi over 2. Second qubit is a 1, it picks up a phase of pi over 2. But now notice that this last stage of the computer, actually two things are happening. You're getting a phase gate on the second qubit, but you're also getting a T gate on the third qubit. So let's look at that. The third qubit is a 1, so you pick up a T gate there. Right? So that'll be this T gate. Then this is 0, this is a 1, so you pick up a T gate there. This is a 0, no T gate. This T gate here is from the previous work, right? So this is a 1, so you pick up this T gate here. And you can see, there was only 3 before, and now there's a 4. You get a 0, no T gate. You get a 1, you get a T gate here. All right, so now we've added all the T gates, and we're very close to the end. We've figured out, we've accounted for everything on these 2 qubits. We haven't done this one. So state 14, the final state, includes this Hadamard, but we haven't addressed the Hadamard yet. But we've addressed everything else. So what are we looking at? Well, first notice that our quantum computer lined up in binary again. Also notice nothing ever happened to this first guy, right? No conditionals ever were added, so you never flipped any bits, right? Because these always started in the 0 state. And even if you did, none of the phase gates would have operated because, so this 0 state always sort of sits still in the middle of all this. I think that's interesting. And also notice that this notion of phase kickback never happened. It never happened that if we were able to introduce a phase, that we could have put that phase somewhere else in this computation. Phase kickback was not a thing in this circumstance. If it was, if I introduced a phase because of some, because of some element of the circuit that introduces a phase, if that phase gets introduced here in this state, it's glued to this state of the computer. It can't be shuttled to some other state. Now, in principle, we could have rearranged things a lot and maybe gotten some instances where something like K-phase kickback could have happened. But the fact that it's all glued to this state is important. And the reason is, I guess it's important to understand why. And the reason is because these states here are not eigenstates of the T operator. The T operator's eigenstates are 1 and 0, not a superposition of 0 and 1. And ultimately, the fact that there's no phase kickback is related to that. We'll be talking a lot more about that in our phase estimation section. So the point is, this is almost the final state of our quantum computer. We're one Hadamard gate away. But before we do that Hadamard gate, let's look at what we've got here. So we've got pi over 4, minus pi over 4, minus pi over 4, and pi over 4. So that is 0. This next one, we have what have we got? We got minus pi over 4, pi over 4, minus pi over 4, minus pi over 4, and pi over 2. Well, the pi over 2 cancels with those two minus pi over 4s, and these two cancel, so that one is 0. Likewise, we have these two minus pi over 4s cancel with that, and then these two cancel. These four obviously cancel. These four obviously cancel. These four obviously, oops, nope, that's not right. These two obviously cancel, and these three obviously cancel. And then in the 1, 1, 1 state, what have we got? We've got pi over 4 cancels with pi over 4. But then we have pi over 4, and pi over 2. So those don't cancel. Those don't cancel. What did those give us? Well, those give us pi over 2 plus pi over 2. So that's e to the I pi. So this whole thing becomes minus 1. Right? So our final state of this whole thing before the final Hadamard gate is this, right? There's no coefficients, there's no amplitudes. Well, amplitude in front of every state is unity except for the last state, which is minus 1. So this is the output of our computer at this point for these two gates. And now we have one Hadamard gate away. So this is an example of how the idea of quantum algorithms, this is interference, right? This is a quantum process that took these gates, took these states, ran them through all these gates, and in the end, you've got a lot of interference going on that ends up canceling all of this stuff out. That's literally how quantum computers execute interference. And in the end, this interferes with a negative number, and these are all 1. Now, what would be in a real quantum computer, this interference eliminates these guys. It drives some of these guys to 0, and it only leaves the answer. So you would have 0, 0, 0, 0, 0, and then 1 for the answer. That's sort of the goal. In this case, you're kind of using interference. I mean, we're just demonstrating the fact that interference is happening. But this is very important, -1, because what are we going to do? Now we're going to start factorizing. I'm going to take this state here and this state here connected by this green line, and I'm going to combine them, and I'm going to factor out the 0, 0 and the 0, 0 for the qubits 2 and 3. I'm going to factor it out, and I'm going to be left with qubit 1 in the plus state, the 0 plus 1 state, and qubits 2 and 3 are in the 0, 0 state. Then I'm going to do the same thing for the when qubit 2 and 3 are in 0, 1. I'm going to take these two, where qubit 2 and 3 are in 0, 1, right? I guess I should do that in blue, right, to be consistent. Right, qubits 2 and 3 are in the 0, 1 state, so I'm going to take this state, and I'm going to combine them together and factor out the 0, 1. And then I'll do the same thing for the 1, 0 state, right? I'll combine this state here, I'll combine this state here with this state here, and I'll end up with this here, where I factor out the 0, 1 and the 0, 1. So now, what have I got? Well, the quantum computer is still in the sum of these three states, plus this last state, where now if I factor out the 0, 0 state, I'm sorry, no, I factor out the 1, 1 with the 1, 1, now this minus sign matters, because you'll notice this final state here has 0 minus 1 in it, right? So these guys end up in the plus state, and this one ends up in the minus state. So qubit number 1 ends up in the plus state in these three sums, and in the minus state for this last one. But what's happened? What is the last step of our process? The last step of our process is to take the first qubit and run it through a Hadamard gate, and a Hadamard gate is its own inverse. So it's going to take the plus state, which is this state, and return the 0 state. It's going to take this one and return the 0 state. It's going to take this one and return the 0 state. And it's going to take this one and it's going to return the 1 state. And so ultimately the sum of these states here is the output of our quantum computer. That state plus that state plus that state. And now you can see how this is logically a Toffoli gate, right? The input qubit number 1, which started in 0, it stays in the 0 state at the end of the circuit as long as qubits 2 and 3 are not both 1, right? That's what a 2-bit Toffoli gate should do. When the qubits 2 and 3 are in state 1, then you flip the first qubit. And now this is highly entangled, right? Because if I measure the control qubit, if I measure a 0, right, this state collapses and this state collapses, and you're left in a superposition of these two states, right? But you will have certainty on your outcome measure. What if I measure qubit number 3? If I measure qubit number 3, this state goes away and this state goes away, and I'm left in this state here, this superposition of this state and this state, the 0, 0 state for qubits 2 and 3 and the 1, 0 state for qubits 2 and 3. What I do know for sure is because I measured a 1 in that third, or I measured a 0 in that third qubit, I know for a fact that the first qubit will be in the 0 state. It is absolutely certain. But I'm not sure about the second qubit. It could be 0 or it could be 1, right? I don't know if I'm in this state or in this state. So it collapses the superposition just enough so it defines the property of the Toffoli gate, but it doesn't tell you the property of the entire quantum computer. Now, likewise, if I measured the target qubit, if I measured the first qubit and I came up with a 0, then this state goes away, right? We know that this state goes away, but it doesn't tell me that much about the two control qubits, right? All I know is the two control qubits are not both 1. It's the only thing I learned. So this is still a very entangled state. Even at the end, you've got entanglement between qubits 2 and 3 and qubits 1. So that's really important. But the point is now you see how entanglement existed throughout this entire process. At any point, if I started collapsing, measuring qubits in here, I start eliminating a lot of states. If I measure, say, the second qubit at stage 6, and I get a 0, well, say I measure the second qubit and I get a 0. Well, then this state's gone, this state's gone, this state's gone, this state's gone. I lose 4 states, but I still remain in the superposition of all these states. So, um, so it's all very sensitive to measuring things. And what we're going to see in our next lesson is we're going to see how sometimes in order to make circuits, you have to add qubits just to get calculations to work. You have to add what we call ancilla qubits. And so when you throw in ancilla qubits that are part of the calculation in order to make the calculation flow, because you're building it out of C0 gates and single qubit gates, but at the end, those ancilla qubits you're using just to help you get through the calculation are highly entangled with the calculation. And so you've got to disentangle them, which is called uncomputation. And we'll discuss uncomputation in our next lesson. So today we actually did a pretty thorough examination of how some gates work. We've kind of demonstrated the decomposed or deconstructed Toffoli gate, which I think was a really good exercise. And next time we will talk about a quantum computer that looks like this. We will demonstrate this is going to be a conditional 3 gate, right? Which means this operation here is going to be dependent on these 3 bits being set to 1. And in order to construct that gate, we're going to need this computer, and we're going to introduce ancilla qubits, and we're going to discuss this part of the circuit, which is called uncomputation. Okay, I'll see you next time.